All right, welcome back. So let's get going on this book. Really interesting video this morning that I'd like to recommend quick. And I do have my new set of, so let me see here. So device audio capture there, input capture line complete one. So I am using a new set of 3M headphones as I just outlined. And they're a little bit different out of the box than the other ones. But anyway, I wanted to highlight this video here, which I thought was pretty interesting. Why I stopped using Jupyter Notebooks. So spoiler alert, he's kind of still using them. He's just using the VS Code features for them. So we could switch to that. That's fine. There's a special setting that he uses for and I'm hearing a little bit of echo is why I'm having trouble speaking now. But yeah, and I hadn't heard that with my other headphones, so I don't know what's going on with that with my other pair of 3M that I used to use. But if we search for interactive, or if we there we go. Yeah, so interactive editor playground. I think this is it. No, I forget what it was. But anyway, I just wanted to bring up this video because we're using Jupyter Notebooks a lot in the series. And yeah, Jupyter Notebooks, they were good for their time, but we're kind of this is the future. So I feel like this is a better solution. This interactive feature in VS Code, or just VS Code more generally, as an alternative, is probably a better way to go. So I don't know what feature this is. Unfortunately, I did watch the video, but you can see the other thing that's pretty cool is one thing I kind of don't like about Jupyter Notebooks is now you're dealing with IP, Y, and B files. You're not dealing with PY files. Like anything that takes you out of Python, I kind of don't like. Like I just like Python is just really well designed to be a human readable, easy to work with language. So why are we using IPNY? Why are we using JSON? Why are we using YAML? Just use Python. If it's not PY, then you're using something less readable and well designed. A Python dictionary, in my opinion, is great. It's just as easy to use, if not easier, than YAML. So that's another reason I wanted to bring this up was it allows you to work directly in the Python file, and then you can get the same benefits for using Jupyter Notebook, but without having to use the special Jupyter file and without having to run a special Jupyter program. You just run it right in your terminal using this interactive tool. Which sorry, I'm actually not able to set up. Maybe it's an extension. Let me see that. So interactive. So yeah. So anyway, just check this video out. And yeah. So he's got so yeah. So anyway, wanted to mention that. So now moving on to use case 3. What different types of SD-WAN devices do I have deployed? And I need a quick break. I'll be right back. All right, I'm back. And one quick thing I have to address is when you put on the 3M headphones, they're not going to sound so great. It's going to sound basically like you're on a landline call. And then you're going to hear everything. It's going to be in monitoring mode. So you're going to hear yourself speaking, you're going to hear the background, and it's going to be in a little bit of a delay as well. So what you can do is disable monitoring mode, go into advanced audio properties, and somehow disable monitoring mode on it. You can use ChatGPT to help you toggle settings. That's basically one of my favorite ways to use ChatGPT. So for 3am work tunes, how can I disable monitor mode where I no longer hear what was received in the mic fed back to the output.
To disable the monitor mode on 3M WorkTunes, follow these steps. Power on the device. Ensure that your 3M WorkTunes are powered on. Access the settings menu. Press and hold the mode button until you hear a beep or see the LED indicator change, indicating that you have entered the settings menu.
Okay.
Navigate to the monitor mode option. Use the volume buttons to scroll through the settings menu options. Look for an option related to monitor mode or mic monitoring. This may also be labeled as talk through or similar. Disable monitor mode. Once you locate the monitor mode option, press the mode button or a designated select button to toggle the setting. Set it to off or disable.
Yeah, so there's a special mode button that is pretty good. And the mode button does different things. It's kind of like video games when you push a button, depending on the context, the button does different things. So I'm not sure. Yeah, so I'm not sure. Yeah, so I guess I'm not sure how to. Yeah, so let's try to look at the manual. And we'll try to look at the manual for the particular model. I mean, it's probably similar for the other one as well, but this is important because when you put these on, you're going to have a little bit of static on the line. You're going to hear yourself talking. You're going to hear your noises. It's not going to be like high fidelity. It's going to be a codec, like a landline. So you definitely want to figure out how to toggle the settings so that you're getting a better sound quality. So yeah, so audio. So this is audio input mode. That means you can use it with a cable. You don't have to use it with headphones. Sorry, use it with Bluetooth. You have the option to use the cable. This is in another language. So yep, we can fit it. We can power it on. We get auto shut off. That's the other thing about these that can be a little annoying. After 5 minutes, it will go into power down mode if it doesn't have like active input or whatever. But it's easy. You just go and spin the wheel on it and wake it back up. That's fine. All right, so I guess I'm not sure how to take it out of this mode. So these are in different languages. So I do have the box. Frequency. So we got frequency mode and we've got recall mode. Yeah, but so this is about the AM FM. So what we want to learn about is the Bluetooth. All right, so I'm not sure. It might need some drivers. That could be a reason as well. Um, so we do have bass boost settings cannot be engaged using external device connected to the input. So the mini subwoofer. So press and hold the AM FM until you okay. Okay, so yeah, I remember doing that. Um, but how do I change the? You can turn vocal assist off. That would be good. Um, frequency spacing. Okay, so that's for the AM FM. Uh, well, shoot. Is there a driver? It's not working the same as the other headphones, and I think it's because of the settings. So let's search for driver. Don't see anything. I don't think the search is case sensitive. No. So 3M Work Tunes driver. Shoot. Okay, so I forget. Shoot, I forget what I did to the other ones to improve the. Um, press and hold the function button. Pairing mode. Bluetooth connection. So yeah, I know how to do that. I feel like it's. Oh, here's the instructions. Yeah, so follow the instructions. There might be some. Yeah, so make sure Bluetooth scanning, searching. You'll have Bluetooth connected. Forward back play incoming calls. See, I feel like it's in call mode now or something like that. Maybe if I close that. Um, shoot. Yeah, you know what? I wonder if I can if I can try disconnecting a call. So if I press previous tracks 3 times, 1, 2, 3, and then press. Yeah, so this is kind of a breaking problem here. We can see this microphone symbol. Well, I am using my microphone. Yeah, I kind of want to move on from this and work on it later. This is a bit of a problem. You do need to adjust this and find the right settings. Out of the box, it's going to be a little bit not ideal. So. Yeah, I guess I could try disconnecting and reconnecting. No, but it's an out of the box thing. Yeah, so it's the headset itself is in some kind of mode that puts it in a codec that is not as good. All right, so the user manual that came in the box, I'm looking at that quick, but as I said, I want to move on from this pretty fast. So we got the batteries, all that. The battery warning, auto shut off, safe volume control. Yeah, so that's good. 80 decibels is the highest you want. Basically any noise. Otherwise, it could damage your hearing. Yeah, there's also a bit of white noise on this, unfortunately, which makes sense because the yeah. Well, that's too bad. I it's gonna take some doing to figure this out. So I'll do that later. For now, it's not preventing me from continuing to read the book. All right, so continuing on. So the pain point for this use case, network and cloud infrastructures may have thousands or tens of thousands of entities, routers, switches, access points, servers, virtual machines, containers to monitor and operate. Frequently, entities of the same type may be configured to run in different roles with different configuration profiles. Sometimes such differentiation may be explicitly based on how we name those entities, with some mnemonics that encode the entity role, etc. However, you could still be in a situation where all entities, apparently part of the same family, may require further subdivision based on their resource profiles because they may have different operational requirements. Ultimately, the challenge here is how we can differentiate those entities based on the data and find commonalities and or differences. By identifying those entities that belong together, we can make decisions about specific operational rules. A very frequent case is when we want to find those commonalities where the target entity is user or subscriber. And I apologize here, this is kind of interrupting the flow of the video, but I've got one more thing I would like to do, which is the device manager, Bluetooth, and see if there's something I can do here to maybe like update the driver here. Automatically, so it's already found it. Already found it. So yeah, I think there's something to do with the driver. I don't know what an S89 Pro is. S89 Pro. A drone? Oh, it's my phone. Okay. So yeah, I thought that might have been I thought that might have been good. So let's look at sound devices. Yep. Okay, and then let's see if we've got a driver here. Best driver already installed. Best drivers are already installed. So yeah, it's that's not it. All right. Well, it's going to take some doing to figure out. I guess I can't stop working on this, but one final thing. Let's do advanced audio properties again. So we've got, we don't need that. So it's the output that we're working with. So let's monitor. Let's do monitor only. Let's do monitor and output. Close. See if that makes a difference. It did not. So we'll change this to monitor off. Okay. Still at monitor off.
For audio input capture.
All right. So yeah, sorry, I have to figure out this out between videos. All right, so the approach. The approach to this type of pain point is to apply clustering techniques that may identify those common groups given a particular set of attributes from those entries. And remember, the pain point is that differentiation between roles with different configuration profiles may be explicitly based on how we name those entries. So it's like unclear. It's unclear like if all devices belong to a similar family. Basically, like the problem is, what different types of SD-WAN devices do I have deployed? It's like how can you group your devices together? It's like, sometimes on the network edge, depending on what your network looks like, you can have multiple different models doing the same thing. So should you group them by the model? Should you group them by the function? They seem to all apply to the same family, but further subdivision based on their resource profiles, because they have different operational requirements, might be necessary. So the challenge is how we can differentiate those entities based on the data and find commonalities and or differences to classify them in an appropriate way. So the approach to this type of pain point is to apply clustering techniques that may identify those common groups given a particular set of attributes from those entities. Those clustering techniques will identify the individuals that are sound check, okay, looks good, closer to each other and automatically identify the groups. Depending on the algorithm used, different parameters may be required. By running clustering, we can automatically group those identified as similar entities, and we can use that information for subsequent operational decisions. Input data. This use case is built on top of the previous use case around multivariate outlier detection. We will use the same data we previously generated with SANS around memory and CPU utilization for all the SD-WAN edge devices. Similarly, a CSV file with the same data, mem and CPU utilization SD-WAN metric.csv, can be used to run the notebook. We could add more variables to make the clustering more interesting, but I wanted to keep things simple to focus on explaining the use case and make more intuitive visualizations. You can try to add new metrics from SANS and make a more comprehensive clustering. As we saw in the previous use case, once processed, eliminated not a number of values, rearranged the columns, our input data looks like the following. So let's open up the Jupyter Notebook. And you know what? Let's just use the Jupyter Notebook. Let's forget about that video I mentioned. It's just easier to do it this way. I know it's probably better to do it the other way, but Look, we even got it running still. So let's go to UCA3, and we might need to make the same kinds of modifications as before since we're not running it in Google Colab. So yep, we got to make the same kinds of changes. So we don't need this anymore, and then we need to change to have it run locally. Okay, and we need to be careful to specify the right path for the files, so it's not going to be UC2 anymore. We're moving on to UC3, so we can run that, and now we got to change the import as well. There is actually a pretty cool way to do that in a different way. We can see if we go to the sans folder. So we don't have a dunder init, but if we add one, then we can create a setup.py file and actually install this as a module and get this to work as it is written here, where we just import sans. We could set it up like that, but I'm just going to do it kind of in the lazy way because this is the only one I'm working with, and this should work as well. All right, so yeah, we got the regular warnings. They're not errors, they're just warnings. We could configure it in a more optimized way. And we can't find TensorRT. I don't think we need TensorRT, so that's totally fine. All right, so now we're going to get to the new metric df part of it. We don't need these other ones open anymore. Might just get confusing. We don't need to save this one. Okay. So we do need to save this one though. So I'll do control there, and I'm not sure if you can. Okay, I'm not sure if you can do autosave. Autosave would be nice, but it looks like you can. All right, so let's get to that data frame. Oh, and we've already got output here, so let's restart and clear all the output. Okay, and then we're getting down to displaying the data frame. There we go. So here's the data frame, and it's not cleaned up yet. So we've got the duplicate entries for each device, and then we've got CPU as not a number with memory filled in for one entry, and vice versa for the other one. So we can just fill in the NaN with zeros and then add the two together, and we get the same value. Okay, so as we saw in the previous use case, once pre-processed, eliminated NaN values, rearranged the columns, our input data looks like the following. So they've already done all the optimizations there. We have therefore two metrics, CPU utilization and mem utilization, corresponding to the 200 SD-WAN devices from the simulated network scenario. All right, so let's do that. So here we're filling in the not a number with zeros. We can see that with this method here. So we can see the results of that. And now we're condensing it down to grouping it by the device name. And then we're adding together the zeros and the real values to only get one entry for each device, and to get the accurate numbers for both of the metrics. And now we don't even need the timestamp either, so we're taking the timestamp out. And there we go. Problem resolution. Our goal is to find what clusters exist on this data set. The assumption, of course, is that we do not know in advance, not even by visual inspection of the data, how many clusters there are. The visualization clearly shows what those clusters are, but we need to find a mathematical or that's a mouthful, algorithmical solution that gives the clustering and classification. So plt.title, let's print that out. Okay, so we've got a bunch of graphs here. The one they're printing out is CPU and memory utilization. So they're printing out all the way down to, so let's just print them all out. Okay, so CPU and memory utilization in SD-WAN devices. So that's going to be one of these. I'm not sure which one, but I'll just print everything out down to there. So here's the memory, here's the CPU, and here's the CPU and memory. And then we've got a utilization there. And one more time, without the, yeah, so this is percent utilization. And here is the total utilization, not as a percent. So we get things are a little bit different there. I think they look about the same. I guess the difference is, yeah, so that's not the difference. It's the same X and Y. The difference is here's a scatter plot, and here is a histogram. The first clustering algorithm in the notebook is dbScan. I will not repeat the explanation here because it is identical to what we saw earlier on the multivariate outlier detection in the second use case. The reason was that dbScan is both valuable for clustering and as a collateral effect for identifying outliers. In this use case, our focus is on clustering, but the methodology and results will be the same. Therefore, I will skip the details in this section for now. Let's jump directly to the second algorithm, k-means. If you remember, k-means finds the optimal centroids for the defined k clusters, so effectively given a number of clusters k. Okay, and I actually don't remember that much about dbScan, so let's have ChatGPT give me a brief refresher on dbScan. So give me a brief refresher on dbScan. Yeah.
dbScan, density-based spatial clustering of applications with noise, is a popular clustering algorithm used in machine learning and data mining. Here's a brief overview. Key concepts: density-based clustering. Unlike partitioning methods, e.g., k-means, dbScan groups together points that are closely packed and marked points in low-density regions as outliers. Core points, border points, and noise. Core point. A point is a core point if it has at least a minimum number of other points, min-pts, within a given distance, epsilon, epsilon. Border point. A point that has fewer than min-pts within epsilon, but is within the epsilon distance of a core point. Noise point. Any point that is neither a core nor a border point. Parameters epsilon, epsilon. The maximum distance between 2 points for them to be considered as neighbors. Min-pts. The minimum number of points required to form a dense region, i.e., for a point to be considered a core point. Algorithm steps: choose an unvisited point, mark it as visited. Find neighbors, retrieve all points within epsilon distance of the point. Core point check. If a point is a core point, i.e., it has at least min-pts neighbors, a cluster is formed. Expand cluster. Recursively visit all its neighbors and their neighbors, etc., as long as they have a minimum number of points, min-pts. Border points. Include border points in the cluster, but do not expand further. Mark values. If a point does not belong to any cluster, not a core or border point, it is labeled as noise. Repeat. Continue until all points have been visited. Advantages: no need to specify the number of clusters. Unlike k-means, dbScan does not require the number of clusters to be specified in advance. Ability to find arbitrarily shaped clusters. dbScan can find clusters of any shape, as it relies on density rather than distance. Outlier detection. Naturally identifies outliers as points not belonging to any cluster. Limitations: choosing epsilon and min-pts. The performance of dbScan heavily depends on the selection of epsilon and min-pts, which can be challenging without domain knowledge. Varying densities. dbScan struggles with data containing clusters of varying densities, as a single epsilon and min-pts may not suit all clusters. Use cases: geospatial data, clustering points of interest. Image segmentation, identifying regions within images. Anomaly detection, identifying outliers in datasets. In summary, dbScan is a powerful clustering method particularly useful for identifying clusters of varying shapes and for detecting outliers in the data. Its effectiveness hinges on the appropriate selection of parameters, which can be challenging but can be guided by domain knowledge or heuristic methods.
All right, so kind of all went over my head, but basically it's a clustering algorithm. Okay, so this all kind of went over my head. Can you explain this to me more simply? Like, I'm not even sure like what a clustering algorithm is or like why it's necessary. So explain it to me in like a fun and engaging way. And in a like using metaphors and like in a way that I can really like understand the why, and I can understand this at a more surface level, like why this would be needed, and like the down and dirty details are kind of not as important for me right now. I just want a general understanding of like when and why this is relevant.
Sure, let's dive into clustering and DBSCAN with a fun metaphor. What is clustering? Imagine you're at a big party. There are lots of people, and naturally, they form groups based on common interests. Some are at the snack table, some are dancing, and some are having quiet conversations in corners. Clustering is like being able to identify these groups without knowing anyone at the party beforehand. You see who's hanging out with whom and naturally figure out the groups. Why is clustering important? In many real-world situations, data is like a big party with no name tags. You have lots of information, but you don't know how it's related. Clustering helps you find these relationships for groups. For example, marketing, grouping customers by purchasing behavior to tailor marketing strategies. Healthcare, identifying patient groups with similar symptoms for better treatment plans. Social media, finding communities within a network of friends or followers. DBSCAN in a fun way now. Let's get back to the party metaphor and explain DBSCAN. Party guests, data points. Think of each guest at the party as a data point. Friend groups, clusters. We want to find groups of friends who are hanging out together. Distance, epsilon. Imagine everyone at the party has a personal space bubble. If two guests are within a certain distance, epsilon, they can easily chat. This distance is our epsilon. Minimum friends, min PDs. For a group to be considered a lively, fun group, it needs to have at least a certain number of people, min PDs. Otherwise, it's just a couple of people chatting, and not a big group. Steps of DBSCAN: find a starting guest, pick a guest and check who's within chatting distance, epsilon. Core guests. If this guest has enough friends around, min PDs, they are a core guest. This means they are in the middle of a lively group. Expand the group. Now, look at each of these friends. If they also have enough friends around, they're also core guests, and the group expands to include them and their friends. Border guests. Some guests might not have enough friends around to be core guests, but they're still within chatting distance of the core guests. They're part of the group, but not central to it. Loners, noise. If a guest doesn't have enough friends and isn't close to any core guests, they're considered loner or noise. They're not part of any lively group. Why use DBSCAN? No need to predefine the number of groups. At the party, you don't need to decide beforehand how many friend groups there will be. DBSCAN figures it out for you. Flexible group shapes. Groups can be in any shape, round, long, or regular, just like real conversations at a party. Identifies loners. It can also identify guests who aren't really part of any group, which is useful for spying outliers in data. When is DBSCAN relevant? When you don't know how many groups, clusters, you should expect. When you have complex shapes in your data, not just circular or square groups. When you need to identify and possibly exclude outliers. In essence, DBSCAN is like being a super observant guest at a party who can naturally figure out all the friend groups just by seeing who's chatting with whom, without needing to know the number of groups in advance.
Alright, so that kind of makes it make more sense. So moving on, and I accidentally opened this application, so I've got to close it. And I don't know what that is. I need to close this as well. Okay, now it's completely closed. So, yeah, so I think, here's the bookmark. Let's jump directly to the second algorithm, k-means. If you remember, k-means finds the optimal centroids for the defined k clusters. So effectively, given the number of clusters k provided as input, it finds what cluster each point belongs to. The first question is, how do we find out k? We previously described the elbow method as a good approach to finding the optimal k number of clusters. Therefore, we need to start applying such a method. Also, let's remember that we had before applied a standard scalar so that the scale of the different variables is aligned. It was already because both are in percentage, so the range is similar. But just in case, it is a good practice. And let's get a refresher. Give me a refresher on the elbow method. Elbow method. Sorry, there are typos here. I'm using voice to text. But what I want a refresher on is the elbow method. ELBOW.
No worries about the typos. Let's dive into the elbow method in a simple and engaging way. What is the elbow method? The elbow method is a technique used to determine the optimal number of clusters in a dataset when using clustering algorithms like k-means. Why do we need the elbow method? Imagine you're throwing a party and you want to arrange tables so that friends who know each other sit together. If you have too few tables, some tables will be overcrowded and others empty. If you have too many tables, some people will sit alone. The elbow method helps you find the just right number of tables, or clusters, so that everyone is comfortably seated with their friends. How does the elbow method work? Choose different numbers of clusters. You start by running the k-means algorithm on your data multiple times, each time with a different number of clusters k. For example, you might try k equals 1, 2, 3, and so on up to a reasonable number. Calculate within cluster sum of squares, WCSS, for each k. You calculate the WCSS, which is the sum of squared distances between each point and the center of its cluster. Think of it as a measure of how tightly packed the points are within each cluster. Plot WCSS against number of clusters. You then plot the WCSS values on the y-axis and the number of clusters, k, on the x-axis. Look for the elbow. The plot will usually look like a decreasing curve. As you increase the number of clusters, the WCSS decreases. However, at some point, the rate of decrease slows down and the plot forms an elbow shape. The number of clusters at this elbow point is considered optimal. This is because adding more clusters beyond this point does not significantly improve the tightness of the clusters. Why is it called the elbow method? It's called the elbow method because the plot looks like an arm, and the point where the curve bends sharply is like the elbow. Steps to fun way I met in a party. You have a party with guests, data points, you should say tables, clusters. Test different table arrangements. You try arranging different numbers of tables, from just one big table to many small tables. Measure the comfort. For each arrangement, you measure how comfortable the guests are by seeing how close friends are to each other, WCSS. Draw a chart. You plot a chart with the number of tables, k, on the x-axis and the total discomfort, WCSS, on the y-axis. Find the elbow. The point where adding more tables stops significantly reducing discomfort is your optimal number of tables. This is the elbow point in a chart. Example scenery: let's say you're trying to group or party guests into clusters. Here's how the elbow method helps. One table. Everyone is at one big table, but it's too crowded. Two tables. Two groups form, and it's better. Three tables. Three groups form, and it's even better. Four tables. Four groups form, and the improvement is noticeable. Five tables. Five groups form, but the improvement starts to slow down. Six tables. Six groups form, but the improvement is minimal. If you plot this, you'll see a sharp bend at 4 or 5 tables, indicating the optimal number of clusters. Summary: the elbow method helps you find the optimal number of clusters by looking for a point on a graph where adding more clusters doesn't significantly improve the clustering quality. It's like finding the right number of tables at a party to ensure everyone is comfortably seated with their friends.
All right, so that's the explanation for that, and I apologize. I need to plug something in. Okay, and this is proving very difficult just to plug something in. Okay, there we go. That wasn't so bad. Yes, it was. Okay, so okay, let's go back. So, as usual, what is the methodology of machine learning? Brute force. Repeat the process many times and see which is good. So that is what the elbow method is about. Run k-means several times for different k values and see which one is the optimal afterward. We are running a loop for different k values. We run the k-means model in each iteration with the variable n clusters, which corresponds to k. Then we create a list of the WSS results for each iteration. So we got to do WSS data append. All right, so that's moving on to the deep DB scan section. And I don't see dot append anywhere. So, oh, you know what? We got to move on to the we're in the k-means section, so we're way far behind. I don't know. I guess the book wasn't showing the plot. I don't see an elbow style graph. And I am on use case 3 here. So is this an elbow style graph where you just got an elbow there? I have no idea. Anyway, this is the cell that we're on. So moving on. Once the loop ends, we can visualize the WSS variable against the k value that is associated. So there we go. So here's an elbow method. So I think this is kind of an elbow graph. So we've got the elbow there. So let's see if we can get that graph to show up. Yeah, so we've got kind of an elbow there, I guess. The intuition on the elbow method is that there is a k value that is closest to the elbow of the curve. It somehow represents the optimal value of WSS, the sum of the squared distance between each point and the centroid for its cluster. As the number of clusters grows, this overall distance tends to be smaller. If k is equal to the number of observations, then WSS will be 0 because every data point will be its own cluster, so the distance to the centroid will be 0. However, there is a value where the gains start to decelerate, which is the curve's elbow, and the optimal K. In our case, K is likely 3. There we go. So new metric DF cluster. This is where we go. So to this cell here. We have run again k-means, but this time with the optimal k value according to our previous analysis. The resulting clustering looks like the following. So now we're going to show the graph, and this is what the graph looks like. All right, and the graph looks the same. So now we're moving on to hierarchical clustering. Hierarchical, right? Is that how you pronounce that?
Hierarchical.
Hierarchical, yep. As expected, since we asked for 3 clusters, we got that. The outliers identified by dbScan are assigned to cluster 2. K-means has no sense of outliers. All elements belong to one cluster, so it has converged to this structure given the K value provided. We will now try another method, which usually works quite well, but since it is very resource intensive, it does not scale well. It may be an excellent method to use with a small sample of the data, a few hundreds of data points. Get a first sense of how many clusters there are, and then use that information to run other algorithms such as k-means or others that may work better at scale. This method is hierarchical clustering, hierarchical agglomerative clustering. The first step will be to generate a very interesting visualization called dendrogram. The dendrogram represents distances between data points and starts aggregating bottom-up distances between clusters. The linkage function from SciPy library will effectively compute all the distances at different layers of aggregation. Then the dendrogram function will generate the visualization based on the output z from linkage. So we're going to see a dendrogram here. Yeah, and that does look pretty interesting there. So let's get it on my local computer to show up. And, okay, so we have a dendrogram there. Yeah, that looks interesting. Let me explain what this graph represents. Every horizontal line represents one cluster. The value at which each horizontal line is on the y-axis, distance, represents the distance between the 2 clusters below the one referred. For example, if we take the top cluster, blue color, this one has 2 subclusters inside. Every cluster gets divided by 2. The value in the y-axis, where the blue horizontal line is, around 380-ish, represents the distance between those 2 clusters. The intuition is that the higher the value, the stronger the separation of those clusters. Therefore, it is likely that they are genuinely different clusters. By observing the graph, we need to find out what is the distance level that seems more reasonable to cut horizontally the graph, and therefore determine which the real clusters are. In our graph, it seems reasonable that this value is somewhere between 100 and 150. And that will result in 3 clusters, as there are 3 vertical lines that will cross our horizontal line. Now, let's assume 3 is the right value. Now we can run the hierarchical agglomerative clustering with that value and get the data points labeled with their corresponding cluster labels. So k equals 3. And then we're going to plot a graph of CPU and memory utilization clusters with agglomerative hierarchical clustering in SD-WAN devices. So I'll advance the bookmark and then run that in the Jupyter Notebook. Oh, and okay, cool. This is good. So we've got an error here, which is good. This will help kind of drive this stuff home. It's good to get errors sometimes because then you have to troubleshoot the error and you can understand things a bit better. So we've got an unexpected keyword argument, which is affinity. So the problem is this agglomerative clustering here doesn't accept this argument. So let's see what the parameters for that are. So let's do a help on it. And let's do the help in the prior cell. So it's not so we're going to do this. Okay, and we can do it in either a prior or a post cell. Let's do it in a post cell. Oops, and so delete that. Delete that. Click on this, and let's do it right here. Okay, so we can see what it accepts is it accepts the sklearn base cluster mixin, which we'll probably have there. It accepts the sklearn base estimator. So I'm surprised we didn't get an additional. Oh, you know what? This is the class. So I think we're using. I think we probably import this from the class. Let's see what we got here. Yeah, so from there we're going to import that. So I think we have to look at the help here. Yeah, so n clusters equals 2. We're going to change that to k. K is defined as 3. So the next one we've got is a keyword argument there. I think that's what that means, but it's unexpected for some reason, which is interesting because I thought that I thought that's what that meant. So that's the affinity. It looks like the metric. It looks like this is meant to be metric rather than infinity. Yeah, so we can see here the default metric is set to Euclidean. So I don't know why it's affinity, but I think it's meant to be metric instead. So let's try that. All right, and now we got something. We got it to run without an error. We've got a output here that looks like something that would be in the book. But let's see if we get the same graph. So we don't need this cell anymore. Let's get rid of it. There we go. And then, yep, so that run. So, yep, everything's good. And now we've got pretty much the same graph. We've got 3 colors there and then 4 different clusters on the graph. So, yep, same thing. The result is consistent with what we got with k-means, given that in both cases we have determined that 3 is the optimal number of clusters. Takeaways. Some key learnings from this use case and the approaches showcased that I would like you to take. There is no one-size-fits-all in clustering either. There are multiple algorithms. Try with some, see how they work and fit in your data. When doing clustering with outliers, they may introduce distortion in your results. It may be convenient to first find those outliers, eliminate them, and then do clustering. dbScan, for example, does that for you, but k-means or others will not, so it is important that you take that step first. Data standardization is important. If you have some variables with much larger dimensions than others, that may introduce a bias in your clustering towards those variables, which may not be adequate. Remember to rescale your data before doing clustering. The methods I have reviewed assume continuous or numeric variables. You might also have categorical variables. There are algorithms that can deal with those and a combination of numeric and categorical. Take that into account if your data is a mix of both types. Further work. There are multiple clustering algorithms to experiment with. I would suggest adding new variables to the scenario and explore some of the other algorithms. Part of that process could be to add categorical variables to learn how clustering may work with a combination of numerical and categorical variables. All right, so on to use case 4, which is how many subscribers will be online in my network next week. Prediction is very difficult, especially about the future. So when we come, and that's a Niels Bohr quote, famous chemist. So when we come back, we'll learn about the pain point. So I'll advance the bookmark there. And yeah, that's it for the video. Thanks for watching. See you in the next one.